Welcome to the third lecture of second unit of the subject Signal and Systems. We have introduced about the basic concepts of the operation convolution, and we have established that for linear time invariant systems it is possible to evaluate the output of the system for a given input if we have the information about the impulse response of the system. The operation convolution is a linear operation, and it makes sense to develop the range of convolution, which is to say what are the values of time that we can expect when we convolve two signals. So suppose for discrete time systems I am taking a signal xn and taking a signal hn, and we are evaluating the convolution of the two. So we calculate xn convolution with hn, and that convolution is denoted by yn. Now let us assume that xn exists for values of time starting at n1 and going up to n2. Similarly, hn starts at say n1 and in time exists up to n2. Then it can be established that the resulting signal yn will range in time from n1 plus n1 and will be having a maximum value of time, that is n2 plus n2. This is of course for the case of discrete time systems. We can also develop similarly about continuous time systems. So this was for discrete time systems. For continuous time systems, suppose xt is a signal and ht is another signal, and we evaluate yt, which is xt convolved with ht. If xt is ranging in time from t1 to t2 while ht is ranging from t1 to t2, very similarly the range of yt shall be t1 plus t1 up to t2 plus capital T2, and this will give us the range of time for which the resulting convolution exists. Similarly, there are three basic properties of convolution operation that we must appreciate. The first is called the commutative property. The first one is called commutative property. Which states that if there are two signals and I compute their convolution, so if I have xt convolution with ht, it is actually equal to convolving ht with xt. So by this we mean to say I can evaluate integral minus infinity to plus infinity x of tau, h of t minus tau d tau, or I can evaluate the integral minus infinity to plus infinity h of tau and x of t minus tau d tau. By simple substitution of variable this can be proved, and which suggests that the signals that are being convolved are interchangeable. We can take any signal first. Second property is distributive property. The convolution operator is distributive in nature. What does this mean? This means that if I have three signals, so I have suppose xt convolution with h1t plus h2t, and this is also equal to, in fact, let me write this on the next line. So this is actually equal to xt convolved with h1t plus xt convolved with h2t, right? So this is the distributive property, which states that if I have addition of two signals, so I calculate the addition first and then convolve, or I can individually convolve with the two signals and then add the two convolved results, which is called the distributive property. Third one, which is even more straightforward, is what is called associative. So the process of convolution is associative as well, which means to say if I have a product of two signals existing, so if I convolve xt with product of two signals, so h1t h2t, so this convolution I can calculate h1 and h2 convolution first and then the result will be convolved with xt, or I can do that xt is convolved with h1t first and the result is convolved with h2t. So it's the operation can be done like this. This is called the associative property of convolution. Now, as far as the range of time convolution that we were discussing, that if a signal is from n1 to n2 and then capital N1 to capital N2, the complete range of convolution becomes n1 plus capital N1 to n2 plus capital N2. This is a concept that has to be utilized while evaluating the convolution of two truncated signals. A signal is said to be truncated in time if there is a value of time after which the signal does not exist, and there is a value of time at which the signal starts. So then the signal is said to be a truncated signal. So let us just take quickly a case of two rectangular pulses of different duration. So by taking different duration, we are actually giving a more generalized case. So xt is of magnitude a1 from 0 to 3. Similarly, ht is a2 from 0 to 1, and I want to convolve the two signals. The two signals are truncated, like xt starts at 0, so it is not existing before 0, it ends at 3, so it is not existing after 3 in time. Similarly, ht is truncated as well. We know the operation. If I say that yt is basically xt convolution with ht, I mean to integrate from minus infinity to plus infinity x of tau h of t minus tau t tau, right? If I want to evaluate this, there are 2-3 things that we will look at. When the signal is there, always perform these operations. It's not as if it is going to be performed only for truncated signals. This operation has to be performed everywhere. So I need to plot these two signals, which means that I need to plot this signal x of tau and h of t minus tau. Then we evaluate the product. This is the operation. Evaluate the product, and then the product is integrated given the limits for all values of time, which means to say I will vary time, I will plot x of tau, I will plot h of t minus tau, I will vary t, and we will see what is the product for a given range of t, and given that product I will evaluate the integration. Integration is nothing else but the area under the curve. So like in case of rectangular, I can directly evaluate the integration, but still we will perform the integration. So for this x of tau is very simple. I can just here it is t, right? So I can just replace t with tau, and I can get x of tau plot, which is the same, which is of same shape as xt is. H of t minus tau needs some concentration. Firstly, I will require x of tau that I can provide it. I will now develop what is called h of tau. So h of tau will be just this axis, but now the horizontal axis is tau. We need to plot h of t minus tau, which I can also, just for understanding purpose, I can write h of t minus tau is nothing else but h of minus tau plus t, isn't it? So I want to plot h of minus tau plus t. Remember, the variable is t. So for that, firstly we follow our procedure. So shifting will be done first. I will draw h of t plus t. So h of tau plus t is something like this with respect to tau, remember. So it is an advanced version of the same signal. The point which was at 0, so this point which was at 0 will become to the left by t, which means it will become minus t. And the point which is 1 will also come to the left by amount of t, which means it will become 1 minus t. But I need to evaluate h of minus t plus minus tau plus t. So for that I just need to reverse this part of the signal. So I can just make the y-axis the pivot and just rotate, take a reflection around the y-axis. It's very simple. But now the points will change. So minus t on the right hand side, which was, will become plus t to the right, and 1 minus t, which is to the right in h of tau plus t, will become negative times in this side. So it will become t minus 1. It will become minus 1 plus t, t minus 1, and it will become t to this side. So now I have these two signals, the x of tau and h of t minus tau, and I'll just perform the convolution operator. So this is the convolution operator. I will also like to draw simultaneously the overlapped versions, and we can appreciate how the various reasons are being considered. So suppose I am considering the first case in which, so I have 2 points, this is q and this is p. So I will take different values of variable time t. The variable of integration, remember, is tau. So I want to plot x of tau multiplied by h of t minus tau. So I will plot x of tau is there. I will just plot h of t minus tau above it with respect to tau and see. So firstly we'll consider the case when q is behind this. When q is behind this. So my p is here and my q is here. If q is behind the starting point of x of tau, which is 0, tau is equal to 0, there is no overlapping. And q point is nothing else but t. And remember, this is basically t minus 1. So if I want to evaluate yt, you will appreciate, which is integral minus infinity to plus infinity x of tau h of t minus tau d tau. If I want to evaluate this, it will be 0 since there is no overlapping for the case when t falls behind 0, which means q falls behind tau is equal to 0. We then take the next value of t in which q surpasses 0. So I am saying that now q surpasses 0. My q comes here. But p is still behind tau is equal to 0. So this axis is tau. And I am plotting x of tau multiplied by h of t minus tau. Remember. So my p remains here. Remember, my p is actually t minus 1. Q is t. If in this case I want to again integrate, so I can write y of t is equal to minus infinity to plus infinity x of tau h of t minus tau d tau. If I want to evaluate, you can look here that the only part that is overlapping is this region, the overlapping of x of tau and h of t minus tau. The magnitude of this portion is a2. So the overall magnitude becomes a1 into a2. And now if I want to evaluate the area, that is to say I evaluate the integration, the starting limits of the overlapping is 0. The final limit will go up to q, and q is nothing else but t. So I can write this that it starts at 0, it goes up to t, because remember this point is t, it goes up to t, and the two are constant. So I can write a1 a2 and I will just find d tau. When I am evaluating this, or when I have said that this is the region, then what are the limits? The limit is that the q is to the right of tau is equal to 0, which means that t is greater than 0, and p is behind tau is equal to 0. So what does that mean? That means that t minus 1 is still behind 0, which implies that t is behind 1. So I can just combine these two right now. Combine these two and write that between 0 to 1 my t remains in this case, and therefore I can directly write that this yt here is basically a1 into a2 into t when time t is in between 0 to 1. Remember, there is no equality at 1. And this is my a1 a2 into t, that is the convolution of x of tau and h of t minus tau for a value of t which is between 0 to 1 and not including 1. We now move forward and we now consider the case that now this 1 minus t, which is the point p, is, this is p, this is q. So now my p is ahead of tau is equal to 0, which means what? Which means that t minus 1 is becoming larger than 0. So which means that t is becoming larger than 1. This will remain to be like this till q reaches 3. Q, which is the last point of h of t minus tau, if it is up to 3, then in that case I will have a product which is something like this. This leg will be t minus 1, this leg will be t. So I am saying that now this t minus 1 is ahead of 0, which means t is larger than 1. But q is still behind 3, which means t is still behind 3. So my next important is that t is less than 3, not equal to, less than 3, which I can jointly write. I can jointly write that this is my time which is starting at 1 and is behind 3. In this case, you can directly see here that the overlapping is the whole area, right? The amplitude is A2. So I can directly write that y of t is integral minus infinity to plus infinity x of tau h of t minus tau d tau. But this multiplication is a1 into a2 because x of tau and h of t minus tau do not vary with tau. And the integration can start at t minus 1, can go up to t in this range, and the variable is tau. So therefore, if I put the limits, I get y of t is equal to a1, a2, a constant for the value when t is between 1 to 3, 3 not included. It's very straightforward. Now we go on and see another case. This case is when q is ahead of 3. When q is ahead of 3, but p is still behind 3. So when I'm saying 3, I mean this. So I have this plot x of tau. I will also plot h of t minus tau here. So I am taking up a case in which it is something like this. So my q is ahead of 3, p is still behind. So what do this implicates? This implicates q is larger than 3, so which means q is represented by t. So t is larger than or equal to 3, and p is behind this 3, which means that t minus 1 is less than 3, which implies that t is less than 4. So I can again just take this combinedly and I can write that I'm taking up a case in which my t is starting at 3 and is behind 4. For this case, it's very easy to evaluate the yt again, because I can still write minus infinity to plus infinity x of tau h of t minus tau, the variable is tau, and I can now write that this integration starts at t minus 1 because this is my p, but when it ends, because if I shade the overlapping region, you can see there is no overlapping beyond tau is equal to 3. So the upper limit remains 3, and the value of the two signals is a1 into a2. My variable is tau. So I can now write that my yt is basically a1, a2, 4 minus t, and when it is so when the t is in between 3 to 4, right? When t is in between 3 to 4, this is my overlapping. This is my convolution. Last case, I think it is by default when t is ahead of 3. So again, this is tau, and this is x of tau and h of t minus tau, and I am saying that the p value is ahead of 3, right? So this is q, This is P. What is P? P is t minus 1. So I'm saying the case when t minus 1 is larger than or equal to 3, which then implies me and gives me there is no boundation on Q. You can understand Q can go anywhere. I am now taking up a case in which t is basically larger than 4 and there is no overlapping. The amplitude, okay, it's say 2, but there is no overlapping. So here the yt is, again I will write minus infinity to plus infinity x of tau, h of t minus tau, d tau, but there is no overlapping. This is 0. There is no overlapping. And this is when my t is larger than 4. So it's always a good practice that whatever the result we have, we express the result in collective manner, for which I can write that my yt is 0 when t is smaller than 0. My yt is a1 into a2 into t when t is in between 0 to 1. My yt is a1 into a2 when t is in between 1 to 3, and my yt is a1 a2 4 minus t when t is in between 3 to 4, and finally my yt becomes 0 when t is larger than 0. So I have these 5 cases which is giving me what is the convolution of the two signals. So what is important here to understand is that whenever we are evaluating convolution, we must plot x of tau, which is straightforward. We must plot h of t minus tau and then check for various values of time variable t. Remember, the integration is in tau, the plots are in tau, t varies. So we'll take all the cases of t. It becomes very simple when the signal exists for infinite duration. But still then also, it is a good practice to plot the two signals involved and then check what can be the result of the convolution. What are the possible values of time t? Because then only it becomes from the graphical representation, not the exact value, but still the ranges become very clear. So it's a very good practice always to plot the signals x of tau and h of t minus tau and vary tau, then see what is the overlapping and then integrate accordingly. So in this lecture we have now framed how to go about solving convolution, and in the next lectures we'll see some more examples on convolution and then we'll proceed further. Thank you.